Yeah, we're streaming. Okay, let's start then. Good afternoon, everyone. So, how is assignment 2 going? Any clear plans, ideas, started working, or? It's okay. Yeah, if you want to discuss the curiosity task, Christopher and I will be here after the lecture, so you can just approach us. Yep. All right, let's start with today's topic, but before we start with actually the scene graphs, let's have a bit refreshing of our memory. So what we had last time, the last lecture, what was the content? Yeah?
Loading object files, like OBJ files.
Yeah, and yeah, formats did we review? OBJ.
And several other formats that were more specified, like binary and loading. Loading like from binary and text to like asynchronous over several different file types. And we call like simple OBJ or something.
Loader, yeah. Tiny object loader.
Yeah, tiny.
Yeah. And do you remember, like, OBJ was pretty readable, right? Do you remember what was it composed of? Like the most important part, vertices, except for the optional.
Like vertices, vertex, like textures and normals.
Yeah, and finally, what was composed?
Can't remember.
So, any ideas? We had vertices, textures, normals, and where put all those stuff to put together. Where, like, what was defined? No clue. So it was, the line was starting with F.
Else we don't answer and make it an exam question. They probably know it by then. No, what was the other?
All right, yeah. So it was faces. Like faces can be different, but in our case we reviewed like simplest possible one, the triangles composed of 3 different vertices. And now let's start by clearing up a few stuff. So the meshes are actually contextual bases for the models, and it's like primarily composed of vertices, edges, and faces. So like 3 vertices are connected to form a face, but it can be more. But in our case, like simplest possible primitive we use here as a face is triangle. And yeah, with vertices we can also have embedded like color, normal, texture, coordinates. And from faces on starts more complex parts like polygons, surfaces, groups, and materials. So any ideas? Does those words say anything to you? So what are polygons, for example? Yeah.
Like shapes.
Yeah, what is the condition?
I don't know, like polygons.
Yeah, they are. Yeah, you are going to the right direction.
I don't really know.
So yeah, it's kind of more complex than triangle. It's composed of several faces, but the condition is that all those faces are located in a single, just one plane. And if we have like several triangles together, we can say it's a polygon. If we don't have a plane, and if it goes to the 3rd dimension, then it's not a polygon anymore. Yeah, surface is. Do you remember smoothing? What did it do? In OBJ we had optional smoothing parameter S, that was it was off in that case, S off, that was the expression. And what did it do? We discussed the visualization of, yeah?
It reduces the amount of vertices in the model, so it like gets less, or like thinking of something else entirely.
Vertices are, there was another thing. So what we have except for vertices? Textures and normals. So what it does is just like interpolates normals and leaves one normal to have like for lighting purposes, to have like one lighting and have smooth appearance instead of having like tiny faces with their shading and having corners visible that sometimes might be very rough for the surface. So this one just like leaves one normal for like several faces, effect in terms of lighting. And surface is actually what we identify with interpolation. And we could group them, for example, for assigning different materials to them, or like any operations that had to be applied to group of the primitives. And we had materials. How were they defined and used in OBJ? So how do we handle this material data? Do you remember? Is it directly inside OBJ, or do we use something for help? Did you look into OBJ since the last lecture? Yeah?
I think there was some external library that was used, if I remember correctly.
Sorry, how was that?
I think there was some external library. That was
Yeah,
used,
yeah.
if I remember correctly.
So it's material library, MTL file, where we had defined each of the materials, and then we could, by using use MTL expression, we could refer to the material to that external file. Yeah, and yeah, it was here actually. Polygons are coplanar faces, and surfaces are like just smoothing group for interpolating normal. And mesh is actually combination of several faces, and the way of combining them, way of connecting them. Actually, yeah, theoretically there can be a mesh where some of the faces are not connected with each other, like for example a tire and a car. It depends on the application, but like generally mesh is considered as like a connected group of the faces. So, and there are like several ways of connecting that. So which of those makes sense to you and which one doesn't? Yeah?
I'm not sure if I'm understanding correctly, but in the one all the way to the right, none of the vertices are the same?
Yeah, actually, yeah, that's true. So the idea here is that we can have edge-to-edge connection between the faces. So they share two vertices, they share the same edge, and we just need to have one more additional vertex. Another way of doing like connection is just a vertex to vertex connected faces, like where they share just single vertex and no edge actually. But there is no vertex to edge connection, because we have just like those coordinates and we are connecting this vertex to something in between that we don't exactly know. So this one doesn't make sense. So we either have to connect them with, like, have to indicate one common vertex or two common vertices to share the edge. Yeah, so this is vertex to vertex mesh, and this is edge to edge mesh, and the third one doesn't make much sense. All right, so we represent them like in OBJ. If you remember, list of the vertices, and then what? If you have like just the data, vertex coordinates, and you want to define the mesh, define what are the faces, how they are interconnected, how they are allocated. How would you do this? So just intuitively, how could you do that? So you have all the coordinates of the points in the space, and you want to define the mesh. Any ideas? How could you structure or organize this data in a meaningful sense?
Nope.
No ideas?
Indices maybe, or?
Yeah. Yeah, it's exactly like what's given here, indexed face set. So we used indexes for coordinates, vertices actually, and then used that indices to construct the faces. So what we had here was that, okay, vertex sound like X, Y, Z, and this is first one. Second vertex, X, Y, Z. And third vertex, X, Y, Z. And then the same for textures and normals. To construct a face, like let's say a triangle, we had to use these indices as kind of pointers to those vertices. Like for example, first vertex, first normal, and like second, and so on, and the third vertex, and like let's say. So we use those indices. So we first define what those vertices are. They have their indices, and to construct the faces, we use their indices to refer to those ones. Actually, I think it's better to show it more. Okay, so this is how it's done in OBJ, but now that... So this one is clear, right? Yeah.
Is this similar to the element buffer object in OpenGL, where you just have an array of indexes and then put them together into your faces in the EBO?
Yes, actually. Usage of indexing, yeah, because you don't explicitly indicate all the values, right? You just use indices as kind of pointers to read it from somewhere else.
From the VBO, yes. So
yeah.
You have the index in the VBO, and you put that in the EBO, and then you have the vertices like that.
Yeah, so the idea, the principle is the same in that case, yeah. But now I have the question. Why do you think this is a smart and preferable way? For example, why couldn't I simply define all the vertices for all the faces kind of like this? Let's say if this is a face, take, instead of writing first vertex, just write X, Y, Z, U, V, and so like, instead of writing that, okay, we use second vertex here, why couldn't I simply write X, Y, Z, like directly indicated which vertices I'm using? So what's bad thing about that? Yeah.
Well, if you have like 2,000 vertices in your object, doing that is incredibly tedious. First and foremost, because you have so many values.
Well. Yeah, it can't be that technically, but yeah, on the other hand, you can write some scripts to generate that automatically. Yeah, that can be a problem, but not the most important one. So there are like some more important problems. Sorry?
Performance?
Yeah, performance is one thing. Like instead of writing one integer number, to write 3 floating point numbers, so you're saving memory. Yeah, and also it's usability, like reusability. When you write one vertex once, you can use it many times in different phases. While here you need to copy these 3 floating point coordinates as many times as you want to use them. And if you change that vertex once, you need to change that everywhere. I will show the example of that. Like, okay, this is one very important point, that performance, flexibility, memory, etc. But there is one more basic conceptual problem. What we want to reach with this one. So we can separate 2 different concepts in this with this technique. So yeah. Let's go on. So yeah, the difference, yeah?
In geometry is kind of like shapes, in topology is kind of the forms of the shape, or am I?
You're going to the, kind of right direction, but more kind of clear difference.
So like the topology is kind of like how things are connected, I suppose, whereas geometry is kind of how it's
allocated in the space. Exactly. That's absolutely right. So geometry is absolute locations in the space, so where those stuff are located in the space, while topology is just how they are connected with each other. So what kind of connections do we have between those elements? For example, topology is the scheme of the underground system, knowledge of how, like which station comes after which one, and where is intersections of the lines, etc. While geometry would be the coordinates, like actual position in the city of each of the station and the lines between them. So it's just like about absolute location in the space and the interconnectedness and relation between the objects. I think it's given pretty well on the next slide. Yeah, so geometry is simply coordinates that where the things are in the 3D space, and topology is how things are connected and they just when they have like shared pointers or not to the same indices, whether they use same indices, same edges or not. But let's get back to this one, orientation. So it's important to think of how vertices are specified when we use indices. So when we have this like face, first vertex, second vertex, third vertex. So this order actually makes sense, and we need to be consistent with that. For example, in this case, we have it can be either counterclockwise or clockwise. So we can have like, let's say this is A, B, and C. Just so we either can have A, B, C, or we can have A, C, B. So either counterclockwise. So first write this vertex here, then write this vertex, and then write this vertex. So the order in which we indicate their vertices is important, and I will explain soon why. So in this case we have consistency, right? We have counterclockwise here, and if you look that one like from that side, we also have like, if you take this as this, we have also counterclockwise orientation here. But in this case, actually, it's not consistent because we have counterclockwise here, but we have like clearly clockwise orientation for this triangle. And in this case, we can say that those faces are consistent, those ones, while those ones are not consistent. And if we have consistency, so if we use the same way, either counterclockwise or either clockwise, doesn't matter, but the same way of ordering the vertices for all the faces in the mesh, we say that this is orientable mesh. But so this one is something that is not really recommended to do, but the question, so why does it matter? So why do we care if we write 1, 2, 3 or 3, 2, 1 or 2, 1, 3? It's the same triangle, right? So with 3 vertices we can define just like one triangle. So why does this order matter? Just try to guess. I don't expect that you have read this in advance or something, just like whatever comes to your mind.
You get different shapes depending on which order you do it in?
Not really, because if you have those two triangles, it's still these two triangles, and why should it matter whether you count this way or whether you count this way? So the thing is that, well, yeah, if we explicitly have normal information, actually that shouldn't be that big problem. But in many of the cases, do you remember when I was talking about these faces last time, I said that normal information was optional because the system can automatically calculate normals without explicit definition of it. But in that case, imagine that, okay, I don't have anything triangular, but imagine this is my primitive, let's say this rectangular object. I can have two normals, right? So the normal either can be from here to this direction or from here to this direction. So they're like two normals, n and minus n. So consistency in this case is needed because we need to know in which direction the normals are facing, and all normals for all triangles should be directed into to the same direction. So I don't remember exactly, so we can use in Unity, I think it's a left-hand rule. It was like this. I don't remember. I think also in an OpenSync graph, it's automatically assumed counterclockwise if you don't explicitly do clockwise. But the idea is that like you should have normals facing to the same direction, and the way it finds out where to direct the normal is the way you order the vertices. So if you had two triangles, like let's say this, and the normal, and you order this clockwise and you order this counterclockwise, this means that the normal for this one will be n facing this way, and the normal for this one will be minus n facing this way. So for lighting purposes, it won't make sense. Did you get it?
Sort of.
So we need consistency in ordering the vertices to get the normals facing to the right direction. Because there can be, for each of the phase, there can be two normals, n and minus n, depending the directionality.
Also, it's very important when you're considering culling, so which side of the triangle is actually drawn.
Yeah.
If you have mixed sort of mesh definition, you're going to have trouble rendering the entire model. Unless you render double the amount, in which case you render both sides. But
yeah, exactly. So if you have that, okay, this triangle defined as facing towards camera, and this one facing like against camera, and you want to cull this, in the end you will have something like structured image that will look very ugly. So if you want to render the triangles that are visible, you have these normals like in a consistent way. Yeah, like here is the practical example from my experience. So what I wanted to do is to render a sphere and then to add some spikes to it. Because like what I'm studying actually is whether presence of thin areas impacts translucency perception. So if you have like these very thin areas, people can see through easily why they can't, for example, in the center of the sphere. So like I wanted to generate the shapes, like first generate the sphere and then generate the shapes with those spikes. So the idea I came up with and implemented was the following, that, okay, I had this mesh, here should be triangles, the visualization tool wasn't very good, so imagine here are like triangular mesh, and the way of adding the spikes was initially pretty confusing, and then finally what I decided to do is to select vertices. So first, like select the points more or less equally and homogeneously allocated on the sphere surface, so to have the equal distance among the spikes. And then what I did is that I just increased the radius coordinates, so I converted it to spherical coordinates and increased the radius coordinate for that point, what meant that this vertex moved up in the space. And then this meant that if it was connected with those ones right here, then in this case, when I moved this one away from the surface in the space, like it created like this kind of edges, and I got this kind of spike. So it was very simple, because in this case I had to just change coordinate of one vertex, and then it automatically was referred for this triangle, for this triangle, for this triangle, etc. But imagine if I had to hard code and explicitly write all the coordinates. I had to change this coordinate for all the triangles, for all 6 triangles, I think so. Change the value here, change the value for this triangle, or like, let's have a look at here. So if I want to change the coordinate of this vertex, when we have indices, I just change the value of it, and the pointer remains the same. It refers to the same part of the memory, so it automatically defines those triangles. But if I had this kind of XYZ definition, I had to do the same change for this triangle, this triangle, this triangle. That was very tedious work. So that's one of the examples how flexible it can be when you use indices. But yeah, just one question about this. So what I did here, is this a topology change or a geometric change? Yeah.
Geometry changed.
Yeah, exactly, because the location of the vertex in space changed, but the way it is connected to other vertices remained exactly the same. So topology is the same, even though the shape and the geometry is apparently very different from that. Yeah, that's more or less it about meshes, and we can actually start with today's topic. So this was kind of fundamentals that I wanted you to have before we started with scene graphs. Yeah, so does anyone remember what are scene graphs and what they are used for? On the last lab, Christopher kind of answered that question, if you remember. So what are scene graphs? Does any of you have any experience with scene graphs, any ideas, or heard just, or what, okay, what they are used for, or why they are good to be used? Just any ideas, what comes to your mind when you hear scene graph? What can it be? Just guess, try to guess.
Kind of like...
I will check the stream again. Yeah, no, it's okay. Yeah?
If you have like a 3D model, kind of like separating different parts of it into kind of their own sort of entities in a way. So like you have like a person, you have the arm.
Yes, if you look at it from one point, like from bottom to top, yes, it's kind of separating. But like if you look from the other point, from top to bottom, what can what does it imply?
You mean like what the hierarchy implies?
Yeah. What is a hierarchy? What is a relation? And from top to bottom, we kind of impose some parameters to everything down the tree. So yeah, it's actually good for defining hierarchy and relations between different objects. Yeah, theoretically you can do it manually, you can code it yourself and do manually, but it's very complicated if you have complex scene. So like a good example of usage of scene graphs can be a human body. So for example, the body itself can be a root node, and the hand or the arm can be the child of it, and the wrist can be child of the arm. So for example, if you have translation of the body, if the body moves, the hand also moves, and if you move the arm, your wrist also moves. And yeah, like if you have very simple thing like in assignment 2, you could theoretically do this manually, but imagine that you have a model of crowd, like hundreds of people or like lots of cars standing in the traffic jam. So it will become super cumbersome and complicated to manage all those things. So scene graph just do that for yourself, for you, like itself. It defines all these relations and all the hierarchy. Yeah, so like it doesn't only imply geometric transformations like translation, rotation, scaling, but we can also spread parameters like textures, colors, like from top to bottom. So yeah, we have code for matrix transformations, so that if I have what to say, like, all right, if like this cover is a parent node, and if my phone is a child node, and if I translate, so move in space this cover, right? my phone also moves with it. So I need just the same translation matrix for the parent and for the child. Yeah, we have hierarchy, and we can use the tree to define how the objects are displayed and apply like textures and materials, etc. It can be useful to write your own, like to define scene graphs yourself and write your own one for like lightweight projects that can be feasible to learn and understand the principles well. But for complicated tasks, it's preferable to use tools. So like many tools come with their own scene graph implementation, like some game engines have their own ones. Even if you remember, one of the 3D model formats had it scene graph support implemented, like embedded. Do you remember which one was that? The one that was kind of standardized, used for web. And we opened that. There was also a possibility to embed some scripts inside. So OBJ was just like kind of mesh focused, and there was more sophisticated one. Don't you remember? It was X3D. So yeah, it can come with the framework itself, but you can use like dedicated scene graph tools like Open Scene Graph, and I'll just like quickly show. So the bad thing about Open Scene Graph is that it's not very well documented. So it's open project, it's being updated regularly, has lots of contributors, but the documentation is very bad. And even like you can export your scene graph configuration in OSG, Open Scene Graph format, but like if you go to the FAQ, the funny thing is that what they say is that there is no specification. So for everyone with knowledge of OpenGL and OSG, they can like simply export it and have a look, and they will understand it. That's what they say. So there is no specification like we had very clear one for MTL or OBJ. So the thing is that documentation is a pretty big problem for this. But other than that, you have like lots of resources. You can download examples from this website. You can have a look at the tutorials. There are some guides that I'm not sure how good they are, but you can have a look. So everything that you might need to know about Open Scene Graph is on this website. So it's kind of, oh, sorry, I thought you saw this. Yeah, so this is a website where you have everything literally about Open Scene Graph. You can download the libraries from here, the examples, and here was the FAQ that says that, okay, we don't have any specification, just have a look and you will understand. And yeah, there are like usage examples. So why is it a good tool and what are the examples of its usage? So like if you're interested in using scene graphs and Open Scene Graph particularly, just have a look at this website. And tomorrow on the lab we will have practical examples, so you will download those stuff yourself and you will have opportunity to play with them yourself and kind of play and see how change in hierarchy impacts the final result. So there are lots of cool examples there. Yeah, I think it's time to take a break and we can continue with the trees afterwards. All right, 10 minutes break.